So for today's office hours, I'm going to talk about two things. I'm going to go more detail about when and how we can use Lhopitals Rule, and I also want to give an example about an optimization problem. So the first question, I've gotten a number of questions about Lhopitals Rule, like when can we use it? This is my theorem. The formal statement is in your book as well, Lhopitals Rule. So we have two functions, f of x and g of x. We need to make sure that they're differentiable near a because we're going to end up taking a derivative. And in the most clear statement, so one case of Lhopitals Rule is that if, when evaluated at that point a, both of those functions are exactly equal to 0, and the derivative of our denominator function is not equal to 0 except possibly at a, then we get that we can apply Lhopitals Rule, that the limit as x approaches a of the ratio of these two functions, f of x divided by g of x, is equal to the limit as x approaches a of the ratio of the derivatives of those two functions. So there are two important pieces here. The first important piece is that in this case, when we plugged in a, we got 0 over 0, an indeterminate form. And the second important piece is that we're considering the limit of the derivative of each of the functions individually. We aren't taking the derivative of this quotient. We are not applying quotient rule. No quotient rule. But that's only one case of Lhopitals Rule, where both the functions are equal to 0. We have this other case, and that's when we get the indeterminate form when both of these limits are going off to infinity or off till negative infinity, because recall, those are two of our other indeterminate forms, as when we have infinity over infinity. So in that case, if we have infinity over infinity, assuming that this limit exists, the limit of the ratio of the derivatives, then we get that the limit of the ratio of the original functions is going to be equal to the limit of the ratio of the derivatives. So that sort of seems like a lot of work. What does this all mean? What does this boil down to? It boils down to the fact that to apply Lhopitals Rule, the functions must be of indeterminate form when applying the limits. So either we have this case 1 where we have f of a divided by g of a is equal to 0 over 0. This is the most common one, and then we can apply Lhopitals Rule. Or if we have the limit as x approaches a of f of a divided by the limit as x approaches a of g of a is equal to plus infinity over plus infinity or negative infinity over negative infinity, then we can apply L'Hopital. So you have to check. And sort of the reason why we have this separated in two different cases is that just plugging in this a value into your function, these aren't actually equal to infinity or negative infinity. It's that the limit is equal to infinity. So maybe that's a technical detail that makes it a little more confusing. But what does this mean in terms of application? So I'm going to do two different examples. So for example, if I want to know what is the limit as x approaches 0, whoops, that's supposed to be a 0, of sine of x divided by x. Well, first I have to check. What happens when I evaluate this at 0? I notice that the sine of 0 is equal to 0. I'm plugging in 0 for x, and when I plug 0 in for x down here, I also get 0. So I get this indeterminate form. And I can apply L'Hopital. So in this example, that means that my limit as x approaches 0 of this ratio of functions is going to be exactly equal to, and I put this little star to indicate that I'm applying Lhopitals rule. It's equal to the ratio of the derivatives. The derivative of sine is cosine, and the derivative of x is 1. And I notice that now, when I plug in my values, I get that this becomes the cosine of 0 divided by 1. The cosine of 0 is 1. I get 1 over 1, which is 1. We solved this previously using squeeze theorem. Lhopitals rule is a really nice way to solve it. Another example would be, let's evaluate the limit as x goes to 1 of 3x squared plus 2 all over x minus 1. So notice that in this case, when I check this, I see that plugging in x equals 1 in the numerator, I get 3 times 1 squared plus 2, which is equal to 5 in the numerator. And in the denominator, I get x minus 1, or 1 minus 1, which is equal to 0 in the denominator. But this isn't an indeterminate form the same way. That this is not 0 over 0. So we cannot apply Lhopitals rule. And in this case, the reason is that this limit doesn't exist, that this shoots off to positive infinity in this case, as x approaches 1 from the negative side, and as x approaches 1 from the positive side, it shoots off to negative infinity. Anyway, so this limit doesn't exist, and applying Lhopitals rule would give us a false solution. So, again, in order to apply Lhopitals rule, we would need to have an indeterminate form of the limits, either 0 over 0, infinity over infinity, or negative infinity over negative infinity. And we should always check before applying Lhopitals rule. And in this case, when you have that check, you can get a limit. Otherwise, you would have to evaluate it using previous methods that we saw all the way back in chapter 2. Next, I want to do an optimization problem. And this is going to be computationally messy, but I think that it's conceptually pretty straightforward. And it's a classic type of problem. Suppose we want to minimize the surface area of a can of volume 20 centimeters. So first I have to come up with a formula. What is the surface area of a can? And we're going to have actually, I should probably pause this.